So far, we've been calculating probabilities of outcomes and events one by one. We've been working with quite small sample spaces, but you can imagine that if you had a sample space with over 100 outcomes, if you had to calculate the probability for each outcome individually, it would get tedious very quickly. So in this section, we're going to look at probability functions, which give us a way of looking and finding the probability of outcomes a lot more quickly in certain situations. So the first idea that we need is that of a random variable. So we're starting with what we know. We've got some random experiment, and it's going to have a sample space S. So remember, our sample space is the set of all possible outcomes. And then we're going to have a function x, and the x comes from the idea that we're doing an experiment. And this experiment is going to match each element of S, so each outcome, to a real number, so we've got our sample space S, and we're going to map via our function x into the real numbers. And this function over here is called a random variable. We're used to having ordinary variables in functions, but we're dealing with random variables here because we're looking at random experiments. So for each element S in our sample space S, we say that x of S is equal to x, where x is some number in real numbers, and we call the range of x the space of x. So our space of x, which we're going to denote with an R, is the set of all x such that for some outcome, when we put that outcome into our random variable x, big X, we get out the real number, little x. So this probably sounds a bit confusing. Take a moment to read through it, but let's look at some examples. So we're going to consider the process of flipping a coin 5 times. And the thing we're going to measure, so remember always that x stands for our experiment. So it's what we measure. It's going to be the number of heads in 5 flips of a coin. So the first thing we might think about is, okay, what is the sample space? Well, our sample space is going to be all the possible outcomes of flipping the coin 5 times. So, well, we might get 5 heads in a row, although that seems unlikely. Perhaps we'd get heads, 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 tails, and so on and so on. If we want to think about what's the size of S, well, we have 5 options, each of which has 2 possibilities. So by what we've learned previously, we know that the size of this must be 2 to the 5. So actually there should be 30 more things in here other than the 2 that we've written already. So we know that the size of S is 32. So now we want to think about what is this R. So let's go back and check our definition. Our R is the set of all numbers where that number is the output of the function x for some outcome. Well, we're thinking about our experiment is the number of heads in 5 flips. So we think we put in an outcome, and out comes the number of heads. And what are the possibilities here? Well, we might get no heads if we get 5 tails in a row. So 0 is one possible element of R. or we could get 1 or 2 or 3 or 4 or 5. So those are the possible numbers of heads that we could measure when we do 5 flips. So this is our space of our random variable x. So now we're thinking about what will happen if we put the outcome heads, tails, heads, heads, tails into our random variable x. Well, x just counts the number of heads, so we have x of heads, tails, heads, heads, tails is just going to be, we've got 3, so that's going to be 3. Similarly, x of tails, heads, tails, heads, tails is going to be equal to 2. So we haven't really done anything very fancy, we've just introduced some notation and some vocabulary, but the basic idea is we're just wanting to think about measuring various aspects of outcomes of random experiments. So one thing to do is to think about when random variables might be useful. For example, what random variables might be of interest to a doctor whose sample space is her patients. So take a moment to think about things that a doctor would like to know about her patients that are not fixed, that are random. Well, there are bunches of things. If you think about the form that you need to fill in if you go to a new doctor, one of the things that you might need to fill in is your gender. So that's a random variable, probably your height and your weight. You might need to fill in your age or your blood type. Sometimes you need to fill in something like the number of previous operations. And maybe you need to fill in a medical aid situation. So all of these are things where when the doctor gets an outcome from her sample space, and here an outcome is a patient, there are lots of different things that can be measured about that patient: gender, height, weight, and so on. And we're going to think about how some of these are different types of outcomes. For example, our height is coming out as a continuous variable, whereas, for example, blood type is going to be one of 8 possible things. It's not continuous, it's discrete. Previous operations is probably discrete, and medical would be discrete, medical aid, but age and weight would probably also be continuous, and gender also discrete. So it's worth thinking about what kinds of numbers you can measure from an outcome in an experiment, and they can be either discrete numbers or continuous. So we're going to talk about that a little bit more. But first we want to have a way of talking about countable versus uncountable sets. So when we started out talking about sets, we just said some sets are infinite, and the sets that are infinite are the ones that are not finite. Now we're going to add a little bit of nuance to that with the idea of countable. So a set R, in which we're usually thinking of this as the range of a random variable, contains a countable number of points if either R is finite. So remember, finite said that there's an integer greater than 0 that maps to the size of the set, or there's a one-to-one correspondence between R and the positive integers. And such a set will also be called discrete. So we're thinking of a set being countable if it has a finite number of things, or if you can count the individual things, even if it turns out that there are infinitely many of them. If R is not countable, then you can't count the individual things. So not countable, for example, if you tried to count all the heights between 1.5 meters and 1.6 meters, you want all the heights in between there, you can't do that. You can't enumerate them. So that's an example of something that is not countable. So if R is consisting of something that's not countable, we will usually call it a continuous random variable. Okay, so we've talked about random variables, and now we're in a position to be able to talk about probability functions. So hold tight while we go through this, because we're going to extend the idea of random variables a little bit. Okay, so we're going to presume that we have a random variable x. So just let's remember what a random variable x is. We start out with our sample space S, and we have some function which maps each outcome in S to something in our set of measurements, which is usually our real numbers. So we've got our set of outcomes, and each outcome gets mapped to something in our set of measurements. Now, our outcomes can be anything. It doesn't have to be a number. It could be a number, it could be a color, it could be a dice roll. So those are our outcomes. But our set of measurements is almost always the real numbers. And then the next thing that we're going to do is, from this set, so from our set of measurements, we're going to define a probability function which tells us how likely it was that we got that measurement. So we're going to take a measurement and we're going to define a function, and that's going to give us a probability. So we've got a set of probabilities . So if we think about what these might be, we know that probabilities are real numbers in the interval 0 to 1. So just to go through this again, we start out with some sample space, which is the set of all outcomes. We do an experiment which enables us to measure something about the outcome. And then we have another function which tells us the probability of the measurement that we just made. So an example, at the moment, a friend of mine just had a baby, and one of the things the doctors do is they measure the weight of the baby, and then they'll figure out the probability of a baby of that age having that particular weight. So if we think about it in terms of this, my friend's baby's name is Teddy, so Teddy is an element of the sample space of all possible babies. Now, x of Teddy is going to give Teddy's weight, which when she was born was, I think, around 5 kilograms, maybe a bit more. So we've gone from having an element of the sample space to having some measurement of our element of the sample space, in this case baby Teddy. And then if you plug that into one of the forms that doctors have, you can measure what the probability is of baby Teddy having that particular weight. Possibly something like quite a high probability. So that's what we're doing. So this is the measurement, and this is the probability of having achieved that particular measurement for this particular outcome. All right. So now we can start to talk about a probability function. We're going to start by looking at a discrete random variable, and then we'll briefly look at continuous random variables. So let's have a look at this definition. A probability mass function, given some discrete random variable x on a space R. Okay, so remember we've got our sample space, and we map via our random variable x to some space R. A probability mass function on x is a function going from R to real numbers with the following properties. So the first property is that for every x in our space R, f of x is bigger than naught. So this is just a little side note over here. If you haven't seen this notation before, this upside down a means for every. So what this is saying is that for every possible measurement, just going to rub out my hand there. The probability is positive. All right. So every possible measurement that we could do has some positive probability of occurring. What's the next point saying? So our next point is saying that if we add up the probability of each measurement that's possible, we need to get a sum of 1. So this links to the sum of all probabilities so the sum of all probabilities of all outcomes is 1. So that's all we're really saying there. If you sum up the probability of every possible outcome in your sample space, then you must end up with a total of 1. And then the final thing that we have here says that if you do if you have a group of measurements, so we're thinking of A as a subset of our set of measurements, so you've got a group of measurements, then the probability of belonging to the group is just the sum of the probabilities of things in the group. It's worth spending some time unpacking this for yourself. We've used quite a lot of notation here. So we've got this new notation over here, this upside down A, which stands for every, or sometimes you'll hear people say for all. We've used some summation notation twice there. We've been using our probability notation, our set theoretic notation. So there's a lot of notation going on here. Just make sure you feel comfortable with it. then one convention that we use is, suppose you get some number that isn't a possible measurement, so x is not in your space R. Then we use the convention of just saying, well, the probability of getting that measurement is 0. The reason that we might do this is that this often enables us to say that the domain of f is all real numbers, which is sometimes going to be useful. Okay, so what can we do with this? Well, let's look firstly at an example of a discrete probability function. So we've got the function f of x over is equal to x over 10 over the space 1, 2, 3, 4. And we want to check, is this actually a discrete probability function? So if we go back, we've got three things we need to check. We need to check that for every x in R, our function spits out something bigger than 0. So our first thing to check is that for every x in R, f of x needs to be greater than 0. Well, let's just check. Our function takes in x and turns it into x over 10, and our R is 1, 2, 3, 4. So we're going to have 1 over 10, 2 over 10, 3 over 10, 4 over 10. So yes, it absolutely does. Then the next thing we want to check, if we go back, is we want to make sure that if we sum up all the values of our function over all the elements of our range, that we get 1. So let's have a look. So our sum over our x in R of f of x is going to be f of 1 plus f of 2 plus f of 3 plus f of 4. And if we add this up, well, actually first let's do the function. So our function puts each of these over 10, so that's 1 over 10 plus 2 over 10 plus 3 over 10 plus 4 over 10. And if you add those up, you'll see that you get a total of 1. Okay, so we've got the second thing sorted. Now we need to just check that this is the case. Well, there's not a lot to check here. We're basically just making sure that if we take any group within our R, then the probability of x being an element of A is given by the sum of the probability of things in our group. And that's more a statement about a probability mass function than something we have to check. So in fact, with just checking these two things, we're done. So this is an example of a discrete probability function. And if we head off to look at our textbook, we can also see what some other probability mass functions look like. So if we evaluate SAGE, so here, if you look at the first block, that's our domain. So we're thinking of the possible measurements that we have. So we've got 1, 2, 3, 5, 6, 8, 9, 11, 12, 14. So those are the possible measurements that we can make. And it just happens that we have got that the probability of measuring a 1 is 1 in 20, probability of measuring 2 is 1 in 20, probability of measuring 3 is 1 in 20, probability of measuring 5 is 3 in 20. So if we want to sketch the function, we can look at the green lines in this image below. And this shows us the probability. So on the y-axis, we have the probability of each of the discrete measurements that we have that are along the y-axis. Along the x-axis. Just for a little bit of interest, although we're not going to really focus on it in this course, if you have a continuous random variable, then you can describe what's called a probability density function, and it follows rules that are similar to the ones we've just seen, but in a continuous way of phrasing things rather than the discrete way that we've seen. We will refer to both probability mass functions, so that's for discrete random variables, and probability density functions, which is for continuous random variables, as just straight probability functions. And mostly, when we're talking about probability functions, these will actually be discrete probability functions.